Hi, students. In this lecture, I am going to discuss problems from Irodov. Let us see first one. A horizontal plane supports a stationary vertical cylinder of radius r and a disc A attached to the cylinder by a horizontal thread AB of length L0. You can see a top view. And initial velocity V0 is imparted to the disc as shown in the figure. How long will it take along the plane until it strikes against the cylinder? The friction is assumed to be absent. Okay, let us see how to start. At first, make the given diagram. This is now cylinder. We are seeing from the top. So this appears to be just like a circle. So having a string now, its length is L0. This is now string. Its length is L0. Attaching here one a particle, I can say disk here. So his intention of disk means it is just like one particle. Now this length that is given L0. Now this is given velocity V0, right? And you are given for cylinder radius is R. So now how long it takes, right? Before it strikes the cylinder, let us see. If you observe throughout the motion, speed of the particle does not change. First focus free body diagram for this one. Now this is on a horizontal plane which is smooth. So its weight mg vertically downwards. That is balanced by normal reaction which is vertically upwards. That means in the plane on the particle, you can see there is no force along velocity. You can see force is only normal to velocity. That is a tension. You can see tension is now normal to velocity. So in this plane, the only force is now tension, and that is normal to velocity. So in that case, direction of velocity changes, but its magnitude does not change. This is what we have learned while learning a uniform circular motion. Because you can see in case of uniform circular motion, that means speed is a constant. Centripetal force is the net force. That is towards center, velocity along a tangent. Angle is always 90. Only magnitude changing, but not, sorry, only direction changing, but not magnitude. So now same logic here. Tension is always towards, sorry, tension is always normal to velocity. So here only direction changing, but not magnitude. So speed is a constant. So since speed is a constant, I am writing here time taken that is equal to distance traveled upon speed. Okay. Relation is speed is a constant. That means now we have to focus what is the distance traveled by the particle. Okay. And distance traveled by particle is now it is length of the path followed. See the path follow. That is given like here path. Given path like this. So we have to find length of this path. Okay. See here what I am doing. Let us take at one instant. Let us take at one instant. So at one instant, for example, string is like this. String is like this at one instant. Let us take let us take normals to the string initially. This is normal to the initial position of the string. This is now normal to the present position of the string. Suppose now this angle is theta and this is now string, okay? And this length equal to r theta. So remaining length is now L naught minus r theta. The remaining length is L naught minus r theta. Or I can say C1, for example. Okay, this point is given as P. Suppose now this is C and this is D. This BC length, arc length is r theta. Now the length of CD, that is now L naught minus r theta. Now here I am taking a small change in the angle. Assume that now this angle changes from theta to theta plus d theta. That means now this will become like this. That means now string will be that a contact will be here, you can say. So it is how I'm taking diagram here. If you draw normal to this length, okay, like this normal, that will be d theta. This is now d theta. That means this is now d theta. Therefore, this also d theta. Let us take in a small time interval dt. The particle has moved from this point to this point. This is now length, or you can say distance traveled. And this is equal to L naught minus r theta into d theta. Because in that small time interval, the length CD is almost constant. So CD, suppose this is C. CD and CE both are same. So ED is now arc length. Okay. And arc length equal to. So CD value L naught minus r theta into d theta. Just like R into d theta. That is now the value of ED. And ED stands for distance traveled in a small time interval dt. Okay. Like this, we have to calculate distance covered. Okay. Then take sum of all those things. Sum of all those things. Then we are going to get distance covered before touching the cylinder. So I have to integrate. This is now ds. Now integrate. Okay. So while taking integration, now we have to focus limits. See carefully when theta equal to 0. So theta equal to 0 means string was like this. Okay. So theta equal to 0. Distance covered 0. Now see how much angle we have to consider. That angle will be, since this length is L naught, it will be equal to L naught by R. Okay. For example, L naught equal to 2 pi R. Then what happens is this theta becomes 2 pi. That means when this completes one round, it will touch. Okay. So it is 0 to L naught by R. Now see calculation. So it is S. So S equal to L naught theta minus r theta square by 2. Okay. Now substitute the value of theta in this. theta value L naught by R to 0. It becomes now L naught square by R, L naught square by R minus L naught square by 2R. Okay. Now see what we get. This is equal to L naught square by 2R. That is now distance traveled before touching the cylinder. Okay. So we got now distance traveled and we know speed is a constant. Therefore, time taken to touch a cylinder, that is equal to S by V naught. That is L naught square by 2R V naught. Okay. That is our answer. So here key point is that speed is a constant. That's why directly time taken equal to distance traveled by speed. So then we are focusing how to get distance traveled. Okay. Let us see next problem. Let's see the question given. A smooth rubber cord of length L, whose coefficient of elasticity is K, is suspended by one end from the point O as shown. The other end is fitted with a catch bead. So here catch in the sense when this is sliding down, now this will be caught. This will be caught by this one, the meaning of catch. Okay. You're having some provision here so that this cannot go directly out of this cord. Getting it? This will come here and it will stick to this point, right? A small sleeve A of mass M starts falling from the point O. Neglecting the masses of the thread and the catch, find the maximum elongation of the cord. Let us see how to start. So make the given diagram. This is now cord. So this can be taken just like a spring while taking elongation. The only change when you are comparing this elastic cord and the spring, for spring we are having compression as well as elongation. Coming to for cord, there is only elongation. There is no compression for cord. Okay, that is the only difference. This is now catch. Okay, so now there is a sleeve. Now there is a sleeve. It is now released from point O. Point O is here. From point O starts falling from point from here. So we have to get now maximum elongation of the cord, right? Then see what we can do. So when this reaches the catch, okay, now that sticks to the catch like this. Now this is having some velocity. Therefore, because of that velocity, this cord starts elongating. Suppose this cord elongates by a distance x. Let us take elongation is x. Okay. That means before the body or you can the particle comes to rest temporarily, elongation of the cord is x. Now see what we can write. The length of the cord is given as L naught. Then the particle has come down by a distance L naught plus x. So if you are taking the particle cord and earth as a system, for that loss in gravitational potential energy mg L naught plus x. This is loss in the gravitational potential energy. This loss converts into elastic potential energy. There is no kinetic energy, only elastic potential energy. That is equal to half k. It is x square. Elongation is x. Now remain just a calculation part. Now see carefully calculation part. This is a kx square minus 2mgx minus 2mgl0 equal to 0, right? So this is of the form ax square plus bx plus c equal to 0. Now see calculation for this means finding roots for x equal to minus b value minus 2mg. So minus b means 2mg minus b plus or minus square root of b square 4m square g square b square minus 4 a value k, c value minus 2mgl0. Okay, right, by 2a value k. Now see the calculation 2mg by 2k. It is mg by k plus or minus. Here having 4m square g square. 4 is here. Mg is here. I am taking 4m square g square outside. That becomes 2mg. 2mg by 2k. It is again mg by k. Root 1 plus minus minus plus. Already I have taken this outside. Remaining is 1. 4 already taken outside. 2 is left. So this becomes now 2k L naught upon mg. Okay. And you can see carefully. We are having here plus or minus. When you are taking mg by k, this is a corresponding to equilibrium position, or you can say net force equal to 0. That means we can see somewhere, for example, when this is called after reaching the catch, somewhere here x equal to mg by k. There net force equal to 0 because mg is balanced by kx. Or you can say this is x naught, mg balanced by kx naught. But it is having velocity. That's why it goes beyond that. That means maximum elongation, that will be mg by k plus this value. So answer is now mg by k plus this one. Okay. So it is just matter of writing this energy equation and remaining just a calculation part. Okay. Let us see next one. See the question given. A small bar A is resting on a smooth horizontal plane, is attached by threads to a point P as shown, and by means of a weightless pulley to a weight B possessing the same mass as the bar itself. So given both are having same masses. Besides, the bar is also attached to point O by means of a light non-deformed spring of length L0. So non-deformed means no compression, no elongation. And stiffness. Stiffness means it is spring constant. That is given as 5 mg upon L0, where m is mass of the bar, The thread PA having been burnt, the bar starts moving. Find its velocity at the moment when it is breaking off the plane. Okay. This is a given data. We have to find velocity at the moment it is breaking off the plane. Let us see. Right, first make a diagram for given, make the given diagram. Now there is a spring. To the spring, we are attaching a block of mass M. Now string is a bond. Okay. Now this is connected to, this is a passing over a pulley. There is a one more block like this of same mass. Right. Now you can see once string is a bond, what happens is this block starts moving right side. Okay. This is A and this is B. Now, when this block A breaking off the plane means losing contact. We can see after some time, at one point of time, you can see the location of block. It is somewhere here. Okay. And you're having elongation of the spring. Spring is having elongation. Okay. Suppose it makes angle theta. Right. Now see what we can do. Spring force, suppose elongation equal to x, then spring force will be, so focus a free body diagram for block A. I am focusing along vertical because it is losing contact. Losing contact means one component of a spring force balances weight of the block. So weight of the block is balanced by one component of a spring force. I am taking x is elongation, then kx is a spring force, kx cos theta. That is now component of spring force along vertical. Okay. Now take the first condition, it is losing contact. Therefore, kx cos theta is equal to mg. Okay. Next, see what is elongation. Natural length, that is equal to L naught, right? And you can see present length. This is now present length, right? So in this triangle, this is now hypotenuse and this is now adjacent side. So this length will be L naught by cos theta. That means elongation x equal to L naught by cos theta minus L naught, right? Substitute that in this one. See what we get. K into now in the place of that taking here in the place of x and the cos is there. So it becomes now you can take here L naught common, L naught into 1 by cos theta minus 1. Okay. Substitute that here. So K L naught into 1 minus what else left? 1 minus cos theta, right? Check with one's calculation. I hope it is correct only. K L naught cos theta, cos gets cancelled, remaining cos here. That is equal to mg. Now see carefully the value of K. K given here, K equal to 5 mg upon L naught, right? That means in the place of say K L naught, In the place of KL naught, write 5 mg. So in this place, write 5 mg. This is a 5 mg. I will write here once again, one more step. So 5 mg into 1 minus cos theta. That is equal to mg. Now see calculation. mg, mg cancel. I can take 1 by here. So cos theta equal to, so what the value of cos theta? It is equal to 4 by 5. That implies theta value 4 by 5 means 37. Okay. Right. Now see what we have to calculate. So when it is losing contact with the ground, we have to find velocity of the block. And remember, we are connecting A and B by a string, which is inextensible. That means speed of block B and that of A both are same. Okay. Now you can see how much distance it has moved. That we can calculate, right? Let us take this distance equal to y. It has moved by distance y before losing contact. That means this also moves down by same distance. That is y. Okay. And from diagram, you can see y value. Y is now opposite side and L naught adjacent side. I can write tan theta. So tan theta equal to y by L naught. Okay. So from here, y value L naught tan theta. Right. So tan value how much? 3 by 4. 37, 3 by 4. Right. Now see what we can do here. Right. Conservation of mechanical energy. It is a smooth surface. Smooth surface means there is no loss of energy. Okay. So this block B is moving down. It is losing gravitational potential energy. So I'm writing here. Loss in gravitational potential energy for block B is converting into kinetic energy for B and A and spring potential energy. So I'm writing here half m v square into 2 because both having same mass and same speed. That's why into 2 plus half kx square and x value how much? See x value how much? X equal in the place of cos 4 by 5, 5 by 4, 5 by 4 minus 1, 1 by 4. That means x value how much? L naught by 4 half kx square. Okay. And remain just calculation part. See calculation part. It is mg in the place of y. 3 by 4 L naught. I am taking this one to this side. Half kx square in the place of k. Substitute now this value 5 mg by L naught in the place of this. In the place of k, I am writing here 5 mg by L naught. Okay. So remaining is now I'm taking that to here. See what we can take here. mg L naught common. Remaining is now 3 by 4 minus 3 by 4 minus it is a 5 by 32, right? 16 and 2 32. That is equal to mv square. Now see that calculation how much we get. V value m and m gets cancelled. V value root of it is 19 g L naught upon 30. Cross check once calculation 19 g L naught upon 30. Now substitute values in this. We get approximately it is 1.72 meter per second. Okay. So here we have taken condition losing contact. That's why force equation along. But second equation, we have to find speed. So we have taken conservation of mechanical energy and remain just calculation part. So I hope you got a clarity.